Good morning, good afternoon. Welcome to Storage Performance Benchmarking, Part 4, File Components. My name is Ken Cantrell.
And my name is Mark Rogov.
And let's just jump right in. So, a brief administrivia. SNIA legal notice. The material contained in this tutorial is copyrighted by SNIA, unless otherwise noted. The big thing to know is you are welcome to use this material as long as you give credit to SNIA for having done so and you use it in its entirety. You should also read the rest of the legal notice. No warranties expressed or implied. Use at your own risk. SNIA has 160 unique member companies, 3,500 active contributing members, and over 50,000 IT end users and storage pros worldwide. You can learn more about SNIA at snia.org/technical or via SNIA's Twitter feed. Okay, as I mentioned, my name is Ken Cantrell. I'm the RTP-based, Research Triangle Park-based North Carolina manager of the performance engineering team with NetApp.
And my name is Mark Rogov. I will work for Dell EMC. I'm a systems engineer, and I'm also based here in North Carolina along with Ken. Now, we were supposed to have Alex McDonald here on the phone as well. Unfortunately, he has technical difficulties, and he was not able to be here. So, but he was going to moderate. We're going to be taking his duties as we're going along. Important things to mention right off the bat. The slides for this presentation will be available right after the presentation is over. They will be available in both PowerPoint and PDF format.
The streamable version of this will also be available immediately afterwards. And shortly afterwards, which probably means a week or two, there will be a blog post that we will work to answer your questions. So I encourage you, if you have questions, use the Bright Talk feature to submit your questions. Without Alex here, we will be looking through them as much as we can and trying to answer what we can during the webcast. But whatever we don't get to, as we have been, we'll be creating a blog and trying to answer your questions in the blog. So Mark, what are we talking about today?
Well, this is our installment number 4 of the Storage Performance Benchmarking series. We've had 3 successful runs before. And let's repeat a little bit of what we've done prior to this to lay the foundation for the rest. In the first session, we discussed terminology and basic concepts of storage performance. Little things like ops versus IOPS. And we also took a look at the graph. We had some fun with it to emphasize a very important point.
Right. So I think one of the biggest takeaways of session 1 was the idea that there is no single metric, whether that's megabytes per second or IOPS or power or floor space requirements that matter.
Or dollar per rack.
Or dollar per rack. The metric that matters is the metric that matters to you in your context. And every customer has a metric that is most important to them, and that's the metric that matters.
And then in session number 2, we introduced the concept of solution under test, which involves everything that's involved in your performance world. That is the clients, the servers, the switches, the hard drives, and everything else. The entire solution under test, or sometimes we call it a SUT, plays a role. It matters. And within that solution,
there's a bottleneck. There's going to be a slowest component.
There's always going to be at least one component that's the slowest.
Right. And what we really wanted to do was tell everybody how to remove every bottleneck from your system.
Except that you can't remove the bottleneck completely. The bottleneck always exists. What you can do is shift it.
And so we gave a few performance principles for how you might be able to shift the bottleneck from one location to another one, preferably a location you don't care about. And again, I encourage you to watch session 2 for the explanation of those principles. And then session 3.
In session 3, we moved into the block world and we gave you the block components. Started with talking about random versus sequential workloads and what the real difference between those two are. And then talked to you about how the disk drives or flash drives are constructed. And then contrasted them and pointed out the differences and similarities between the two.
And we did that in part, mixing this idea of random sequential and block devices, because flash drives and hard drives care differently about sequential versus random or versus read versus write. We were trying to help that be clear to everybody which one's better suited what their benefits are.
So we explain the RAIDs and a little bit of erasure coding as a superset of what RAID was.
Right. And then today.
But all of that was done as a foundation. Reason why we have to have 3 different sessions was to lay the foundation for something. And what do we use foundations for? To build on. And we would like to build our file presentation on the foundation of block knowledge. So what we're going to talk today is file and file system performance. And here we have a picture of file systems, but before we get there, I went to Wikipedia. I'm sure many of you can do the same thing, and you will find that Wikipedia lists 245 file systems.
And we are not talking about 245 different file systems today. We can't do that.
So Ken, if we're not talking about 245, what are we talking about today?
Right. So in general, we talk about file systems living in at least in our world, 2 major places. File system could live on your client, so you have like an NTFS file system or an ext3, ext4 file system. You have a file system living on a remote device, a network attached storage. And so we're going to talk about file systems in both of those contexts, but we're going to do it like up a level in the terms and concepts that apply whether it's a local file system or a remote file system. So we're not going to talk about any file system in particular, the general concepts that apply to all file systems, and particularly the aspects of file system performance.
All right. So we're just talk about the file system and things that apply to all of them, regardless whether they're local or NAS.
Right. Now, there may be some aspects that some weirdo esoteric file system, but yes.
So with that, let's just go over briefly on our agenda, and then we'll take a look at the question and then move on from there. So the agenda for today is to talk about the file system fundamentals, the layout fundamentals. Then we'll talk about file system operations. We will move over to file performance in the file-oriented world and explain what we mean by that. And then we also will finish with a series of graphs, and we'll walk you through what we think about those graphs and how to get to your conclusion that matters to you when you look at some data like that. And let me look quickly at
There are no questions. You can keep moving.
There's a question 1? Nope. Okay. So moving on into file system layout fundamentals.
What's a file system, Mark? If we're going to talk about file systems in general, what is a file system? When did we really start talking about file systems?
The term file system, Ken, was coined in 1964. I read that in Wikipedia, therefore it must be true. But the reason why file systems are put in place is because when data is organized on some media, let's say magnetic media, whether it's tapes or drives, let's kind of go back in the last 60 years of computer history. And in the blocks world, we have block with data. So what we have to do is seek to the correct block, read that block, and then go seek from the next block and so forth. It's a little difficult to organize that information. So file systems were thought through, and you can think of them as a library. If a file is a book, then looking for that book in the library requires some sort of an organizational system. And that's what file systems were brought in to be. If we look at the picture of the file system, it's a typical Unix file system structure that I'm sure a lot of you are familiar with. And we look at the file A, which lives underneath directory Ken, which lives underneath directory home. All of that structure is a way to organize data so you can get and find the information you're looking for. But to do that, in the library world, you would be using something like an index card to kind of look for the book.
Yeah, showing our age there a little bit, talking about an index card. But the idea is that in a library, whether it's a card catalog and there's an index card, or it's somewhere online, then we're going to have data that tells us about our book. Right? Our book isn't just the information we care about, what things I want to read, but there's information like the title of my book, the author of my book, when my book was created, maybe even a checkout history of my book. We would call that metadata. It's data about data. It's data about our book. And the same concept applies in a file system, that a file system is holding the data we care about, our files, which is like our books, but then there's information about our files, the metadata information about our files.
And we place those little gray boxes on top of every object visible here in the file system tree to emphasize that the metadata exists for every one of those objects.
Right.
There's a record where we explain what that is. And similar like with books, that's where the name, the type, the permissions, the access times, like we in library cards. If anybody still uses index cards, you would hear a list of who checked out the books last. Same thing happens here in the metadata. And there's pointers to the blocks that contain data that are in that library. So going back to the library thing, it's not just because you're going to get to the book, but you're also going to find a trail of where those pages live because they can be living somewhere within the library itself.
So a very, very short excerpt on this in that we're showing the metadata associated with every file. How and where you store that metadata, it may differ for file systems. Some may store it exactly with the file. Some may store it in different places in the file system. But pretty much all file systems are going to have a way of keeping track of both metadata and the data for a file.
So running in the scenario of, hey, we need to get to file A. How do we find file A? How do we get to it and start reading from it?
Okay, so let's set this example back up again real quick, just make sure everybody knows where we are. We have a file system. We have a file, file A. We know where file A is. What does it take to read the contents of file A, or even to know where the contents of file A are?
So we start all of this with a path. We know where file A is, but we need to get to it. So how do we find that file effectively? How do we walk that path? And we start that from the root. The root is the top level of any file system. And we start from there. We look the metadata of the root. And that metadata, was, as we said, consists of name and some other things. And it's going to consist of a list of all the objects in that level. So in this case, there's going to be objects for etc., dev, home, and so forth. But besides just having those names, it's also going to have a pointer to where the metadata for that name lives. So the next one we're looking in our path is home. And when we look at home, we're going to get the same metadata, similar metadata as we have for the root, except it's going to be about home with its own name and so forth and attributes and mode bits and so forth. And a list of objects underneath home with their names and pointers to where metadata for those objects lives. So let's follow that path all the way through to file A. I'm going to kind of skipping a level of Ken because it's repetitive. File A also has metadata, and that metadata is very similar to the directory metadata, except it's going to have pointers to the data blocks where the directory would have pointers to names. And we look here at data blocks. I painted them in red to show you that we're seeing where the data blocks live on the file system.
And so I love this picture, in part because part of what this picture is showing is that those data blocks aren't sitting in this picture right next to one another. Is that on purpose?
It is.
I guess I know it's on purpose. We made the chart. But why is it doing that, Mark?
It's doing that because we actually don't control where those data blocks live. It's up to file system. There's placement algorithms within the file systems that dictate where data blocks is going to show up on the file system.
Right. So remember,
and sometimes they can be together, sometimes they can be not together. It's up to the placement algorithms.
Right. So remember, a part of what a file system is doing is it's taking information that we care about and it's linking it together in a way that makes logical sense to us. So it's putting all the parts of a file together and making it look like a coherent, logically sequential whole. But there's no reason that that data actually has to live next to each other on the LUN itself, on the disk itself. And so that magic of how a file system is laying out data on disk, that's part of what I call the secret sauce for various file systems and various file system vendors. Some file systems might be oriented towards writing data out initially, and optimized, or some might be optimized for reading data back. Or
some might be optimized for random workloads, some might be optimized for sequential workloads.
But
that's where they differ. That's not the only difference between them, but it's a big part of the difference between those file systems. And so, besides the fact that file systems decide where everything lives, it's important for us to recognize that it's abstraction layer. Within the scope of one file, from the application point of view. We don't see where those blocks live. We think it's sort of a contiguous stream of data. And the file system provides that structure
Right.
to make it simple for applications to perceive the world.
And so the other takeaway to this, file systems are providing structure because a file system has data and a set of metadata that tells us about our data, and that metadata isn't necessarily static. Something's going to be creating it, something's going to be modifying it.
Something's going to be accessing it, just looking at it.
So let's use that then. We have no additional questions at this time, so we can keep moving through and look then at file system operations and what file system operations are and how they relate back to this data metadata idea.
All right. On the file system operations, let's take a look at the simple user command and say, hey, I am writing some text string into a file. I'm sure most of us on the phone have done something similar to one or another. And it's a simple, really simple command. But when we look at that command and what it means in terms of file system operations underneath it, we're going to see 4 distinct file system operations that will satisfy what's being said here.
Okay, so let's stop here for just a second. I have a user who's doing one thing. The user says, I want to echo some text stored in a file. And under the covers, the file system is doing more than one thing. Here you have it doing 4 things.
4.
Right, it's doing 4 things. And why, how do you know these are the 4 things it was doing?
I know these are 4 things because I ran this command on my Linux box and I used strace and I found them up verbatim.
Okay. So why does it take 4, right? What are these 4 things doing in this example?
Well, now when we know how file system structure is provided, we can decipher this relatively easily. We have to stat and find out, do we have access into the current directory where we're going to write the file? That's what's happening. We don't have to find anything here because we're already in it. Then we have to open the file and say, hey, we're opening the file and creating it at the same time. Then we have to write the word test, which is 4 characters, into that file and then follow that by a close.
Okay. So is my takeaway from this what? That every file, every user level work is going to do 4 operations under the covers?
Well, it's ironic. It's ironic you say that. That shouldn't be the takeaway. The takeaway should be that every user command can take multiple file operations. It just happens to be that the reading and writing is very similar in essence. If we took the second command here is a read from the very same file. It's also taking 4 operations. But yeah, it's multiple. Sometimes you don't know what it is.
Okay.
Now, notice how the read here is very, very similar, except for the operation in the middle that says read instead of the write. It kind of makes sense. But still, we have 2 metadata operations up front, then a read, and then a close, also a metadata operation. What's going to happen with a delete, Ken?
Now delete I like. Delete's kind of fun. So RM, if you're not a Unix guy, RM is a version of Del, deletes a file. But what it does is it doesn't actually modify data in most file systems. It actually, in most file systems, it's just changing metadata. So what you get is you get a stat call that says, am I allowed to modify this file? And then you unlink it, which really means you're unlinking the metadata from the organizational structure of the file system, which makes the file look like it's gone.
So you remove those pointers to the red blocks that we have in some slide elsewhere. Those blocks still exist, and they still have the same data.
In most file systems.
In most file systems.
Right.
In most file systems.
So part of I think our big takeaway from this is that user-level work, whether it's reading a file or writing a file or deleting a file, these simple user-level actions have file system-level implications. And there's not necessarily an intuitive one-to-one mapping that says, I'm going to do this at an application level, and it's going to cause this to happen at a file system level. So but there is definitely file system operations that happen for our user-level actions of working on files. So is this it? I mean, are we good now? We have our 6 different operations and...
No. There's actually 108 file system calls that a Unix file system defines. Unix operating system defines, I'm sorry. So we're only concentrating on these 6 to emphasize how they run with simple commands but there's a lot of them.
Right. And so if you're wondering, some of those others are things like making directories or removing directories, changing the attributes of a file.
But let's think about it a little one step further. So we said block I/O was a foundation. How do these file operations can interact on the block level?
It's a great question, and I think it's not even just on the block level. So I'll answer that question, but let me make this comment too, in that every one of these operations, file system operations, it's doing something, right? Because it's doing something, it's going to use at least CPU. But it's likely that they're going to be doing block I/O as well, right? If I don't have the metadata for a file already in memory, and I'm going to do an echo test, I have to go and get that metadata from disk. So this thing that I'm doing that I think is a write operation, from my mind, I'm creating a file, I'm just doing a write, in reality is going to be doing a read as well, not of data, but of metadata.
So you're using the structure of the file system and the fact that it's abstracting some of the stuff away from you by means of these file system operations that you don't get to see often. So in the first example, we have the echo test. It's a seemingly write command. However, you do see that one of these calls is an explicit read. Similarly, when we are reading a file, we're finding that one of those calls is a write.
Right, and I think that's not intuitive for a lot of people. You would think if I issue a read command, why am I ever doing writes? But in this case, the close would be modifying. Why is it a write?
Because it's modifying the metadata.
Right.
And that needs to be stored on disk.
Right.
Now, it may not happen immediately, right? It could be cached away at some systems, and the system could flush that modification later on.
Right.
But it will still end up being a write I/O to the disk at some point in time.
You've colored some of these.
I colored some of these, yeah.
Open and unlink is both red and green.
Yeah, those are interesting, especially open. Again, I encourage anybody to go ahead and read the man pages on open. But open operation has flags, and one of those flags is create, which is a write when I'm creating a new file. Or it could be just a read when I'm just reading the file. That's why open command can be both an I/O write and an I/O read. And same thing with an unlink. Before we can unlink something, we need to have data. What are we unlinking? So we need to be able to get to that.
So this has been focused right now on local file system operations, but we said back kind of at the beginning that we wanted to talk about ideas that were relevant to both local file systems and remote file systems. So think of SMB or NFS, for example. So here's what I did, Mark. I had my laptop sitting, which it happens to be Windows 10, sitting on my corporate network, and I had my home directory that was mounted via SMB, and I wanted to create a file in my home directory. So I
don't know why you would ever do that, Jeff.
Right, so for the purpose of our example, I wanted to create a single file with 3 spaces in it. I popped up a Wireshark, and I traced and I looked at the SMB commands necessary, which are file system operations. It's remote file system operations necessary to create a single file with 3 spaces in it.
Okay.
So I know you know the answer, so it's not quite as much fun, but which one of these would you think was representing the number of SMB operations I saw when I did a network trace creating a file that just had 3 spaces in it?
Well, we just looked at the local file system example and looking at the file system operations to create a file there. Granted, it wasn't 3 spaces, but a very similar example. So looking at these 3 bars, I would have to say it took 4 in the local. I would start with 6 being the remote number of SMB operations to do it on the server somewhere else. 2, unreasonable, that's just not enough. 104, ridiculous. Clearly ridiculous.
And I think that would be a great guess. It'd be a great interview answer for me. But in reality, each one of those, so I actually created the file in 3 different ways. I traced all 3 of them. So in the first one, it was blue.
Whoa, that was sneaky.
Sneaky?
Sneaky.
The first one was PowerShell command. The second one is I just did an echo from Windows as opposed to an echo from Unix as you did. And in the last one, it was Notepad, and I saved the file from Notepad.
Who would ever use Notepad again?
Well, so what's actually happening is, because you probably see this in almost every Windows GUI, first time you save a file in Notepad, it pops up a file picker window. And so as you start to type out the file name that you want to save the file under, Windows is trying to be really, really helpful. And so with each new character in the file name, it says, ooh, hey, does that file exist in the directory? Oh, hey, does that file exist in the directory?
And it does that for pretty much every character that you start adding.
It started
with data.txt, so you D looks at all the Ds,
right.
DA looks at all the As. So what are you trying to tell me, though, even though Notepad is insanely ridiculous, the operations that constituted that 104 were not reads and writes. They're all metadata-driven operations of making sure you don't step on your own toes.
They are. I don't remember the exact count, but somewhere like around 102 of those are what's in that directory, basically, or do I have access to that directory? And it was only the last two that was writing the data in the file and closing the file. And so what's the takeaway from this? The takeaway from this is not don't use Notepad. The takeaway from this is there's a lot more ops than just reads or writes in the file world. And it's non-intuitive how your user-level actions, like using Notepad or Echo, are going to translate to the file system level operations. But everything we do that touches a file is going to translate to file operations at some level in the file system.
So in other words, in the block world, there's also different operations, but what you're going to see is predominantly we'll look at what's going on in the block world. It's mostly about reads and writes. You see other operations, but they only take time. There's not many of them, and they're kind of far from
Seek. I'll add Seek in there.
Seek as well. But in the file world, we see all operations in large quantities at all times. And in the case of Notepad, we have the metadata operations overwhelm everything else. There's only one write in there.
Right, and that's a great point, because the really important part out of this is that every single file system operation is going to take memory and CPU and possibly cause disk I/O. So they're not trivial. They're actually things that have to be dealt with and have to be accounted for. So we had just a couple questions come in. Let me stop for just a second. One of them was asking, how do I capture the actions on a file?
So on the Linux command, I'll take the Linux one. There's a command called strace, and most Linux boxes have it. And if you have Ubuntu, I think you can install it really quickly. And you will run that before you run the command. So something like strace echo text into a file.
I'm actually going to defer most of the answer. There's a couple other ones. I use FileMon on Windows. If you're going to do it with Wireshark, then there's a couple things that you'd have to know about how to take a network trace. But we'll try to get all three of them, and maybe some more if we know a couple more documented in the blog.
Word of caution on the strace real quick. If you're going to run that for sure on the Unix environment, you're going to see a couple hundred lines of text, because your binary that you're executing, like remove or less or echo in that case, is using some libraries. So you need to filter aloud and look at the bottom of the output, and that's when you're going to see real file I/O operation that's relevant to what you're trying to do. So we've simplified the output here to be just about the I/O that we're causing with the data we're saving.
There was another question, how did PowerShell get away with just two operations? I actually had the network trace in the appendix for that, and I think I killed it.
Yeah, we did kill it. It was a surprise to us, too. We didn't expect it, but that's what happened. So we encourage you guys to do it again and take a look at that. At the end of the day, if it was 2 or, let's say, 4, which would be expected, compared to Notepad's 104, it's not a big difference.
All right. So the takeaway kind of at this point, just to go back and summarize, is that our file system is an abstraction layer and a way of handling both data and metadata. We use a set of file system operations that modify and look at both data and metadata. There's a lot more than just reads and writes in this world. So let's ask the question then, what is performance in a file-oriented world affected by? So we'll look at kind of 3 major areas.
So we will look at performance of different file operations. Now when we know there's a lot of them, and we talked about how it's not just reads and writes, let's take a look at what the performance of those operations is and how to decipher it. We will move over and talk about what happens when you have lots of objects. So you deal a lot more with metadata than not. And last but not least, we'll look at a little bit of caching. So with that, let's go and take a look at this graph. And Ken wrote an application.
He calls it an application. I call it a Python script. It just ended up being a little bit longer than I expected. And I do have permission. I'll probably post this in the blog as well if anybody wants to recreate any of this work.
But the point of that application was to run through creating a relatively small number of files all the way to 500,000, actually a little bit more, and take a look at what we can capture in terms of application view of the world performance.
Right. So
we timed every single iteration so we can graph it out here. So what are we looking at here, Ken?
Right. So let's talk about that timing issue again. So let's say at any one of those data points, let's pick the 40,000 data point. What we measured was how long does it take to create, and in this example, they were 8K files, or 8 kilobyte files actually. So how long does it take to create all of those files? And that was one measurement. How long does it take to read all those files after you read them back?
Yeah.
How long would it take to, out of order here, to LS them to get a directory listing once you've made them? How long would it take to unlink them? And so that's what we're looking at, and let's kind of break them into parts.
All right. And here what we're looking at, Ken, is we're looking at creates, overwrites, and reads. And what am I looking at? Can you just walk me through?
Sure.
Please.
So the reason we're looking at just the creates and the reads is that this would be the closest equivalent to like I/O in a block world, in that there is metadata involved in this. I still have to open the files, but there's not much. Really, what we're just looking at here is it's about the same amount of metadata for both of these. So what we're looking at is the difference really between read and write performance. And so my takeaway from this is that pure reads and pure writes, even in a file world, have different performance.
Which kind of makes sense. I think we talked about it in previous sessions when we talked about storage controller caching in the block world. And it's common, I think, between us. We deal with this all the time. The writes can end up faster because they don't hit the disk immediately. They kind of sit in cache. And you see it here as well in the local file system.
Right. For
perhaps the same reason, but that's not as interesting. By the way, if anyone is asking a question about the dips in these curves, just wait till the blog. The dips are irrelevant, but this is live data off of a live solution in the test that we've played with.
It is extremely reproducible, which is why I was willing to do it. No matter what time of day or what day of the week, I got.
But we are not going to speculate why those dips are there, even though it might be interesting.
All right. So that was reads and writes, and I had the reads and writes there, like I said, because those were meant to be data operations. For me as a user, I was thinking I want to get access to the data. What's the difference in performance? So then we looked at unlink or delete performance.
Well, unlink is interesting. We just looked at unlink, and we've determined that unlink is a metadata operation. It actually doesn't do anything with the data.
Right. And so that's why I have this here, is because what I wanted to say was, okay, if I want to read a bunch of files, I want to write a bunch of files, or if I want to unlink them, which is still an operation I'm doing to every one of them, how does it compare? And what I see is that it's a metadata-focused operation, and it turns out it was much, much faster than my data-focused operations.
Which kind of makes sense.
Yeah.
It is faster to unlink something than to actually read or write in 8 kilobytes of data.
Right. So,
but it still linearly grows as number of objects goes up.
It did. So the question I think that you might ask then is, okay, so I have a general idea how much data operations were costing in this solution under test. I have how much a specific metadata operation was costing. Does that mean that all metadata-oriented I/O costs the same? It has the same performance? So that's why I added LS in, because LS is still getting some information about every file in the directory.
Well, LS is really, really fast.
It takes
me
much
10 seconds to delete 500,000 files. It takes me no seconds to list them. That's fantastic.
Yeah.
Can I get one of those systems, please?
So the point of this is not why unlink and LS are different from one another. The point was that even though they're both fundamentally metadata-oriented operations, they have very different performance characteristics. And I'm gonna generalize that out a bit more to the idea that all of our operations have a cost associated with them. And in general, those costs are going to be different from one another. And if we don't understand, going back to the section we just did, how my user-level application is converting into file system operations, I'm really going to have no idea what the performance of it should be or what the performance of it could be, because all these different operations are going to have different costs.
So having a whole bunch of unlinks and LSs on the wire, if we think about SMB, is going to have an effect on overall performance if we compare that to a whole bunch of reads and writes.
Absolutely. And from a user perspective, lots of times what a user's thinking of is, how long is it going to take me to read my data? But maybe if the reads were just a tiny bit of your workload that you were doing, because there was a lot of creates or unlinks, that's pretty important.
So LS is always going to be fast, right, Ken?
Absolutely, Mark.
And it's always going to be the same, too.
Absolutely. You've already changed the slide, so not.
All right, so in this slide, I'm looking at it, and I see 3 different curves. Are you claiming those are all LS curves?
This is exactly the same script running in the same manner, basically, but we ran it under 3 different solutions under test. And
so we can kind of open up a little bit. Those are 3 laptops.
There were 3 laptops running
because these are all local file systems. And what we're looking at here is that the time it took to list files was different for every single one of those laptops. That's bizarre. So not only each operation has its own cost, that cost varies depending on the solution under test.
Which makes perfect sense. There's a reason there's 245 different file systems. There's a reason there's different operating systems. And you get different performance for different operations in different solutions under test.
So the secret sauce is not only in placement algorithms that we mentioned, but also how the file systems treat other operations. So some of them might be tuned a lot deeper to specific operations and not just one thing of where we place the data file, the data blocks. Very, very interesting.
So our takeaway from kind of these 2 things put together would be, you've got to know your file system operational mix, because all of our file system operations have different costs. And that's not entirely true. You might have some that have the same cost as another, but in general, they're all going to have different costs.
So to emphasize the difference in cost, let's just blow it out of proportion. And I think this is where we started to, this is what the next slide is about. When we look at your 540,000 8 KB build files on the left here, and we will have to create those, we have to read them back, we have to list them, and then we have to delete them. And we timed what that took. And then Ken and I looked at each other and said, what if we compare that to the same exact amount of data from the user point of view?
Right.
So 540,000 times 8 kilobytes is 4.1 gigs.
Right. So I'm of the opinion, I think most people care about data. They don't really care about this idea of metadata. They have data that they want. And so, but how you organize that data in a file system matters a lot. So you can see, we've called out before in I guess some of our dry runs, like the LS. It took 12 seconds to do an LS of 540,000 files, 8 kilobyte files.
Which arguably is at least pretty good. Or it could be bad. It depends, right?
Honestly, it was a whole lot faster than I expected. I was expecting much, much longer. But it took 0.0007 seconds.
Or 17,000 times faster to list a single file.
Yes, it was 17,000 times faster to list a single file. So we said this, but I want to restate it kind of for clarity. Why is the left side so much slower than the right side, Mark?
It's because we have file system abstraction layer in the middle. It's because we have the metadata. Every single one of these files has metadata operations with just one file, and possibly the directory metadata where that file lives. And then we have one more and one more and one more. That starts growing. We have a lot more metadata file operations when we look at 540,000 objects than we do have with a single file, where we have just a few metadata operations and a whole bunch of normal block I/O.
So even though we're dealing with exactly the same amount of data, that ratio between data and metadata was very, very different, and it changed the total number of operations that we did. And
it completely changed everything, and the times was pretty bad. One of the solutions that was test took 2.5 weeks to complete this entire test.
Now, before we move on to out of the slide, I want to talk for a minute about the implications of this. So kind of what are the implications of this? Well, the implications could be that for file system performance, the number of files in a directory matter. The number of directories in your file system might matter. The size of your files could matter. So there's a lot of different things that come into play with file system performance. Move on to the next one for just a moment. All right, caching.
So it's another thing. It's not about file system per se. It's more about the solution under test. We touched on caching before, or we said caching exists pretty much at every single tier of solution under test. And how does caching affect everything?
Right. So let's say this. File system designers have learned that working with metadata is bad. At least from a performance perspective. We have to deal with metadata. We have to update when a file was last modified or created. Or
which would prove it again on the screen right now.
We could, but so we've done a lot to try to keep people from having to go to disk. And so caching in this world might mean that after you update a file, you don't flush the information to disk immediately. What it means here is what we did is, actually the purple line is the numbers we've shown already, really. And so in those, we were measuring how long does it take to do the very first ls in a directory. The first time I've gotten into this directory, how fast is that? So
kind of set the stage there. This is when we didn't have any information about the file system of those files cached.
Right. So I actually, again, this was my laptop. I had an external USB drive. I removed the USB drive. I unmounted it and then I remounted it. So the file system knew nothing about it. And I said, go look in that directory. So there was nothing there I could use. The cached ls was when I did that a second time, basically, without clearing anything, without unmounting it. And so you can see a huge, massive difference in ls performance versus when it was cached and uncached. And again, what does it tell us is this is not the fact that cached is better or uncached. Oh. It's also telling us that the order of your file system operation plays a big role. If you have your cache loaded effectively, the data was loaded in cache, and you're addressing that data loaded in cache, the performance is going to be relatively fast. But if your operation is not using data in cache and wants to load new data in cache, your performance is going to suffer. So when we abstract this out and say in the file world, in the workload, if your operation is jumping from one directory to the other, to the other, to the other, trying to read listings of those directories as they go, caching is going to be ineffective for that kind of process. You're not going to get the benefit from it. Your performance is going to perhaps degrade, as opposed to something that says, hey, look, I just loaded data in cache about this particular thing. Let me work in that space and not have to cause the cache to be invalidated. That's a great example. Operation ordering matters too. As if you were just in a directory and you decided to do an ls of it, if you created the files in that directory first and then you did the ls, it might be faster. So we're actually okay on time. I'm going to do a terrible thing and go off script for just a second from where we normally are, because I think this is relevant to benchmarking. We see people in a file world try to recreate things like they might in a block world, where you just create a single directory and then they put some files in it and they try to access those files. Then they move to a real world application where they had hundreds of directories and hundreds of files, and even though they think they're doing the same thing, I'm just reading data, they get very different performance.
So you're trying to attack DD method.
I am. I'm going to hit DD a lot harder later. but that idea. So what affects performance in a file-oriented world?
Just the three things, right?
Well, there's a lot more. but let's at least recap these for everyone real quick.
All right. So the first thing that we talked about is the differences between operations themselves. Each operation has its own cost, and mixing them up makes a difference. Next one is the scale, number of objects in a directory, number of objects in the file systems, number of files, and so forth. That multiplies the effect and the differences in these operations. And last but not least is caching. How effectively is caching being used? Plays a big role in performance in the file world.
It does.
And there's a lot of other things as well, but these three we wanted to really mention before we move on to the next section.
Okay, so let's stop here for just a second. We've had a couple questions come in. Some of these I won't be able to deal with today. We will try to hit them in the blog. The last one asked, is the LS sorting files? Is it statting the files? Judging from the uncast chart, it looks like it's using the default LS options. If you care, this was a Python script. I was using the OS module, and I did os.lister. which is faster than the default OS call. I actually have results from calling out to LS itself, which the person who asked the question, you would probably guess, is actually slower. So the Python lister call is optimized to not get a lot of stat information on it. It just gets the file listing. So it's a bit faster.
Yeah, the other thing that I kind of add some colors is for you to homework to think about. We also had, we were comparing at some point LS with stat commands, and stat was executed right after the LS. And it was an interesting idea there to realize that if you're statting the last file in the directory, to get to that file, the whole process of finding that file, like we walked in the beginning of the presentation, takes the same amount of time as listing every single content in that file, because you have to walk through that list in inodes, going down to the last object in there.
All right. You did a scary thing. You just threw out a new word we never mentioned before. You used the word inode. So we didn't really say it today. As we were talking about the metadata for a file system, one of the most common implementations of file systems would use the term inode and index node to refer to what we were calling like the card catalog.
Like an index card. But the inodes don't exist in all file systems. It's common, but not everywhere. All right. Well, that was a heck of a lot of theory.
This theory and some practice of real numbers. But
so let's do some fun. Let's have some fun. What are we looking at next, Ken?
All right. So, Mark, I have 2 performance charts for you. You need to make a purchasing decision, probably. Which one is better? Tell me which one to buy, Mark. 2 performance results.
All right. Let me see what I'm looking at here. I'm seeing an orange and a blue line. And Ken, are you?
You are vacillating, Mark. I want you to make a decision.
You're pulling my leg in here.
Which one of these is better?
You're pulling my leg in here. There's no Y or X axis. I don't know what I'm looking at. But perhaps you have this graph upside down for all I care.
It seems like you're making excuses. but you're right, right? I don't think I should ever give you a chart that doesn't have an X and a Y axis. One of the reasons that chart is there is because I'm digging at somebody locally. You should never give anybody a performance chart that doesn't have a labeled X and Y axis, because it's really, really hard.
In the file performance world.
I'll say any performance world myself. I think you should always label. But
all right, that's how you labeled it. Okay, let me take a look at that. We have operations per second on the left, and we have iterations on the bottom. Okay, let me kind of think. And you still want me to know which one is better?
Absolutely. Which one's better?
All right. Well, Ken, I live in a world where response time is more important than what it used to be before. So can we redraw this response time on the y-axis to be a little more informative to me and understand what's going on here?
Sure. So we now have it. I've done what you've asked. Super fast. Wasn't that amazing? I've done what you asked. I now have a chart for you that has response time on the left. So the higher you are, the worse you are. You want to be
assuming small response time is good.
I can't imagine the situation. And then total operations per second is still what we were looking at before. It's just now on.
Well, this now looks even worse, Ken. What is this big squiggly line thing? The blue turns sideways like I suggested, except that it's now all elongated and it goes backwards. What kind of performance chart is this?
So here's the deal. We put this in here because it's fun. This is real. This is measured off of a real system. Pretty much every real system I've looked at. It's not true for all. There are some that deal with this better, but pretty much all systems, they're going to hit a point where they are maxed out. And if you try to ask them to do more work after that point, they start queuing things up and they start spending more time trying to figure out what is it I'm supposed to do than actually doing work.
So if we pull back a little bit what we said about caching, the data that they cached becomes less effective. They're overwhelming their cache, slowing things down, possibly. Not necessarily the only reason what's happening.
Yeah, there's a bunch of things that can go on.
But if they were writing on cache and cache was helping, when it's overwhelmed, you're going to see this shoot back.
Yes, right. So there's
response time and
that your cache example, that's what happened here. In this one, the client actually ran out of physical memory and started paging to disk. And so the client stopped asking for things very quickly.
So the response time went up and the operations per second went down. Somebody applied the brakes.
Right. So what most people would do in a thing like that is they would just cut off the end of the chart. So let's just cut off the end of the chart. We'll pretend it never happened, and I never tried to go too far. And so now, Mark, I'm going to ask you again, and hopefully you'll actually answer my question. Which one of these is better?
Okay, well now this chart looks a little more familiar. We have response time on the left, operations on the bottom. The blue chart clearly has more operations and has lighter response time than the orange. So I would want to say blue, but I keep that reservation because I need to understand, what is this showing me? Is that a workload? And if it is a workload, what kind of workload is it?
All right. So
because here's my thought is, let's assume it's the same thing, but orange is 4 times cheaper than blue. Then I'll pick orange. I need my context.
Okay. So yeah,
which matters?
I was kind of expecting you to ask me something like, which one's more expensive? So I'll throw you a bone for a couple of these. This is exactly the same solution under test. The only thing that was different was the workload. So I changed the workload on you between the orange and the blue. Same cost, same system, same client, same solution, just a different workload. So I'll ask, which one's better?
Well, in that case, I really need to look at those workloads and see how do they relate to workloads that I have in my organization.
So, you notice I've been showing you total ops. To help you out, I'll show you more than just total ops. I'll show you the total and the reads and the writes. That gets a little messy. So why don't we
get a little messy.
Break it out. Let's just look at the orange.
Okay, let's look just at the orange.
And so what do you see with orange? You see that.
Well, let me tell you what I see before you tell me. What I see in the orange is you put the formula in there that the reads and writes equals the total. So I look at it and see, okay, well, the reads and writes, the reads are a little bit slower, but there's a lot more of them. There's a little writes are faster, but there's not that many, and then the total kind of adds up. Makes sense to me. This looks like a block workload. Like this is something that doesn't do a lot of other operations. So can we look at the blue one?
Hold on. So this workload, you're right. This workload happened to be the emulation of a online transaction processing database. And so
it's actually, a database workload.
It was a kind of database workload. There are other kinds of database workloads, but this was definitely a database workload, and it was actually derived from real traces of some real databases.
Okay. Let's see on the next one. Let's take a look at the blue.
It looks exactly the same.
Right. Blue is off, Ken. Are you sure you got the right numbers in here? Because if you add the reads and the writes together, there's nowhere you have the total.
Right.
Is something else is missing? Are you playing with me?
Absolutely. It's fun. So why don't we move to the next chart? So here's the deal. This workload is a lot more than reads and writes. I graphed the stats for you because this workload was actually 70% stat calls. But when we add, if you look at everything else, it's reads and writes plus stats, plus commands to open and close files, plus commands to remove and create directories, create, delete files, access checking commands.
So this one has my normal reads and writes and then a whole bunch of metadata operations, which contribute to that total. The writes and the reads, if you look at them, they're kind of high up there compared to the total, but the total amount of data that's moved with this workload.
Don't go there. The total number of operations per second.
Thank you. The total amount of operations per second is pretty high with a low response time, but all of that is metadata type of workload.
Many of them, most
of them.
So
this is clearly, we have all those operations. This is file workload. Now it's not as blocky as the other one. So which one is it?
Right. So let me back up for just a second. The orange one is still, both of these are running from a client across NFS v3 to a remote file server.
Very
interesting. File-oriented workload.
Just the first one doesn't do any metadata.
Right. The first one was emulating the database running across files. This one is an actual emulation of a software build environment. Somebody who had a very, very large source code base tree and who was then doing compiles against it. And again, it was a workload that was created by a modeling, an actual tracing of real customer workloads who were doing that kind of stuff. Statistics from different kind of vendors, or from different vendors who were looking at it.
All right. So now when I know what those are, this is what information I had to pull out from you like you were a real vendor for some reason. And I would say that for me, from the role that I'm playing, I'll go with an orange because it's a database that matters the most. Even though originally I thought blue was better because it's low response time. Blue has nothing to do with Oracle Rack servers that we have in our environment. Nothing to do at all. It looks better and faster, but it doesn't have anything to do, and it's irrelevant. So the orange has some meaning to me. I can now figure it out, and perhaps you can take it away.
So what you're telling me is that database workloads are more relevant in a file performance context than software build workloads.
No, they're more relevant in the file performance context for people running databases over file protocols.
Oh, it is very different. That's a very different.
It is my workload that matters to me.
So the workload that matters is your workload, whatever that workload happens to be. So I'm gonna bash on DD for a minute. So are you suggesting to me that if I were to go and get a valuation of a storage box of some kind, that if I'm a software build environment, for example, the best way to evaluate my storage array is not necessarily to go and get DD and run it in a single directory against a single file?
It's not. No.
Okay, but what if I run 5 of them?
Still, you're doing just reads, let's say it's unidirectional.
What if I run 100 of them, Mark?
You can do 1,000 of them, Ken. They're still going to be just block-oriented type of I/O without any metadata associated with it.
Right. So
in reality, it's maybe a little tiny bit of metadata, but nothing close to what a software build does, where, as we've seen, 70% of that workload, if not more, is metadata type of operation workload. So you can get your numbers from running DD, Ken, but those numbers will mean absolutely nothing for you to understand how that particular solution or the test will perform in your environment.
Right. So I'm picking on DD, but it's not. The point isn't really to pick on DD. The point is to kind of pull everything that we've been saying for the past 40 bit more minutes, I guess 57 minutes together, into the idea that file workloads have file operations in them. There's this non-intuitive mapping. I think it's non-intuitive for most people about a user-level work and how it translates into file-level operations. And different user real workloads, software builds, electronic design applications, database applications, they have their own unique mix of file operations. And because file operations all have different performance characteristics, because they can be cached, because operation ordering matters.
Because it's not just reads and writes in there.
Because it's not just and that's the great one. It's not just reads and writes. The workloads that matter are the workloads that matter in your environment.
All right, let's take a look at the questions and finish up.
There are no additional questions.
Wow, we're either really, really good or we really, really didn't hit it this time. So what we have done today, this was installment number 4 of our series. We have another one on the horizon. We're hoping to do that one on the workload definitions, and we will announce it whenever we're ready for it. To close off, as we said originally, the PowerPoint and the PDF of the slides will be available. They probably already are available on the SNIA website, snia.org/forums/ESF, Ethernet Storage Forums, and you can find the little thing about that. The recording is going to be available on BrightTalk as well. We will look at all the questions and answer them in the blog forum. You can follow us on Twitter. There's a handles. And it was a pleasure talking to you.
Almost done. Not quite done. I'm going to throw this out. This isn't the day job for Mark or I. We do this because we enjoy it, and we think people are finding it useful. The very first one of these we did has been wildly successful. A lot of people have viewed it. If this is valuable to you, please rate it and let us know. Add comments into the comment stream so we can understand what you're finding valuable and what you're not. Your ratings help us to justify to our management why we're doing what we're doing. So rate them honestly, rate them ethically, but if you like it, it really helps us for you to go ahead and rate them, and especially to put your comments in to let us know what's good and what's bad. There are a couple questions that came in since it's 59
minutes.
I guess we're done.
well, let's take a look. We can go a couple of minutes longer, I think.
Okay. So one of the questions was, are there any of these workload models available for download? There are. So the workload definitions that we were using here are the workload definitions from the spec SFS 2014 workload definition. Mark's going to put them up here. You can see them. We didn't think we had enough time to walk through them in today's presentation, but we'll put more information for them up on the blog. Each one of these workloads, so those are actually software build and then virtual desktop infrastructure, which is a steady state of virtual desktops, VDA, which is video data acquisition, and then the database workload we talked to, and then
we're proposing that we're working
looking
on
at a new EDA, electronic design application workload. They're all very, very different. They're all taken from real customer data and real
workloads, real applications.
Real workloads and multiple.
Many of them.
Right. And I was going to say multiple companies working together to create those definitions.
Yeah, that's right.
All right.
All right. Well, thank you very much for attending. It was definitely Ken and I's pleasure to entertain you tonight and share some more knowledge, and we were hoping to see you soon.
Thank
you very much.